This will be my quiz solutions for quiz 9 for Dr. Harley's Tuesday section, and this is a quiz related on the partial fraction decomposition week of Z transforms. So let's get to it. Consider an LTI system specified by the following transfer function, determine its difference equation. And what you should always do is just simplify as best as you can. So I want to do a common denominator for this 4 and see what's going to happen. And you'll get h of z equals 5 minus 4 times 1 plus, how should I write this? 0.25 c to negative 2 over the denominator. So 0.25 c to negative 2. In the numerator, what you'll see is this is just 1 minus 4 times 0.25. That's just minus z to negative 2 over 1 plus 0.25 z to the negative 2. And how you should think about this when you get a difference equation, it's sort of flipped. So these are your x's and these are your y's basically. And any of these z to negative 2s are just time delays. So if you write this out, starting the denominator with the y's, you'll get the 1 goes to y of n, and then you get plus 0.25. And this z to negative 2 is your time delay, so you get y of n minus 2. And then you go back to the numerator, equals 1 goes to x of n minus your time delay, x of n minus 2. And your answer is done right here. This is an acceptable form. You can move the other terms. You can do just y of n if you want, but it's the same thing. It doesn't really matter. Next, draw the pole zero plot of the LTI system. Is the system stable? So let's just start the sketch. And first thing you do is figure out its poles and zeros and poles. So this is related to what you have above here. And you can see that your zeros are obviously at z equals 1 and negative 1 to solve that problem on the numerator. And then your poles are where the denominator equals 0. So it's equivalent to asking when is c to negative 2 equals negative 0.25, and you'll get that it'll be the square root of 1/4, and you'll get that'll be 0.5j. I'll write this as c equals 0.5j and negative 0.5j. So when you draw this out, you'll get a 0 at z equals 1, a 0 at negative 1, and your poles at halfway in the imaginary line, 0.5, 0.5, 0.5, negative 0.5j. Next, is this system stable? It is definitely stable, yes. How do you know this? Because if all the poles, their magnitude is less than 1, it's automatically stable. And in that case, yes, because their magnitude of the poles inside the unit circle, yeah. Otherwise, if any of the poles, their magnitude is greater than or equal to 1, this would be unstable, which we don't have. So your answer's done. Next, determine the output y event for an input x event equals 4 cosine pi over n. How you think about this is you think about the relationship between the z transform and the DTFT is that, well, first, you want to consider h of z, which is related to e to the j omega hat. And in this case, omega hat equals the frequency of the input pi. And this is equivalent to saying, well, h of z equals e to the j pi equals negative 1. So practically, you just need to consider wherever h of z equals negative 1, substitute z equals negative 1 everywhere in your transfer function above. So when you have h of z equals 1 minus z to the negative 2 over 1 plus 0.25 z to the negative 2, you're going to plug in z equals negative 1, and the denominator is 0, and whatever's on the numerator is 0, the denominator is non-zero. So automatically you get h of 0 equals 0. So what this implies is that if y of z equals h of z times x of z, and this part is 0, then that means that y of z equals 0, which is equivalent to saying y of n equals 0, and you're done. Next, on the next question, this is the, let's see, consider the partial transfer function for a system h of z equals 1 minus 0.5 z to negative 1 over this, determine the impulse response h of n. So since this is the partial decomposition sort of week, you kind of know you need to do that right away. So what you'll need to do is, okay, h of z, well, we'll just ignore writing that. You'll say this is 1 minus 0.5 z to negative 1 over 1 minus z to negative 1 over 1 plus z to negative 1. And you need to get to a point where it splits apart and you can take the inverse the transform very easily to get the impulse response. So this will be a over 1 minus z to negative 1 plus b over 1 plus z to negative 1. I'm not even sure why I write these parentheses. Okay. Next, you know, the denominator, fix up the denominators or multiply by the common part, and you'll get 1 minus 0.5 z to negative 1 equals a times 1 plus z to negative 1 plus b times 1 minus z to the negative 1. This is where you sort of have your option on how you want to do partial fraction decomposition. So if you do it differently, it's not really a big deal. You can even plug it to your calculator. So let's just say I want to cancel out this first term a first. So let's say let z negative 1 equals negative 1. Okay, in that case, this left-hand side is 1 plus 0.5. That'll be 3 halves equals b times 1 minus b times 1 minus negative 1. That would be 2b. And what you'll get is that b equals 3/4. Similarly, if you say let z negative 1 equals 1, you get 1 minus 0.5. That'd be 1/2 equals a times 1 plus 1 is 2a. So you get a equals 1/4. So at this time, your solution is looking something like h of z equals 1/4. Let's see, times 1 over 1 minus z to negative 1 plus 3/4 times 1 over 1 plus z to the negative 1. Is there a formula sheet for this? So when you take the inverse t transforms, these are sort of easy to see for this first one because we see so often, but it would be this one. And what you'll get is that this is when you take the inverse t transform. So just choose any color. We get that h of n equals 1/4. So a is equivalent to 1, so it'd just be u of n plus 3/4. This is a positive, it's actually a equals negative 1, so it'd be negative 1 to the n, u of n, and this would be your answer. Next, just to check through. Okay, determine the output signal y of n when the input signal x of n equals delta of n minus delta of n minus 1 is entered into the system. Okay, so what you need to know is that y of z equals h of z times x of z. And in this case, x of z in terms of the z transform is equal to 1 minus z to negative 1. And so you just kind of plug in based on what you have before about what h of z actually was. So h of z was 1 minus 0.5 z to the negative 1 over 1 minus z to the negative 1, 1 plus z to the negative 1. Multiply this by x of z, 1 minus z to the negative 1. And you'll see the cancellation. This cancels. And at this time you have 1 minus 0.5 z to the negative 1 over 1 plus c to negative 1. And you can just split this into 2. So you can say, well, this is 1 over 1 plus c to negative 1 minus 0.5 c to negative 1 over 1 plus c to negative 1. And let's see, can I write this any proper? I just write this as y of z. And this is y of z. Take the inverse z transform here, you get y of n equals, in this case, if you separate the z transform table, a equals negative 1. So this is equivalent to saying negative 1 to the n u of n minus 0.5 negative 1 to the n minus 1. And you know it's n minus 1 because there's the negative 1s right there. So the time delay u of n minus 1. And that would be all for the solution. That's it. And that's the whole quiz.